If you wake up in the middle of the night, do you have to put on glasses just to check the time? What about reading glasses when you just want to check your phone? Or maybe you just want to follow your heart rate while you're out for your morning run. Imagine how hard it is to drive when you're farsighted and you must use your reading glasses to see the dashboard, but not to see the street. We propose a novel display technology which adjusts itself to compensate for visual aberrations. The goal is to improve an individual's visual acuity without the need for eyeglasses or contact lenses. Tailored displays, as we are calling them, transfer the displaying information to the focal range of an individual. When this focal range goes from infinity to close to the eye, we say that the subject has normal eyesight. When the focal range shifts towards the viewer, we call this myopia. A normal display outside this focal range will be blurred. However, a tailored display uses a light field technique to move the image plane closer to the viewer, bringing it inside the focal range. When the focal range shifts away from the eye, any information closer, such as an ebook reader, will become blurred. In this case, the tailoring process moves the image away from the eye and back inside the subject's focal range. With no moving parts and built from off-the-shelf components, our tailored display allows us to address the main causes for loss of visual acuity worldwide: nearsightedness, farsightedness, astigmatism, and presbyopia. In fact, since the inputs of the tailoring process are a wavefront map to represent the refractive errors of the eye and a cataract density map to point scattering sites, our solution can correct for higher order aberrations and cataracts. We use the cataract density map to avoid light pass with unpredictable scattering, reducing glare and halos to the viewer. An eye with higher order aberrations, such as coma or keratoconus, have a different focal range for each position on the cornea. Our tailoring process divides an object into pieces and places them at several depths. Each piece emits light for a specific section of the eye. These splitted light fields are then naturally integrated into the retina. Since we are using multiple depths for each focusing plane, we say our device is not only multi-focus, but also multi-depth. We evaluated two tailored displays. The first one uses a dual stack of high-resolution LCDs, while the second uses a high-resolution LCD with a lenticular overlay. Snoopy here is tailored for a 3.25 myopic view. This image is quite tiny in a regular display, and the subject is only able to see a rounded blur. On our device, however, he receives an improved image. Here is another case. A 2.5 myopic subject with nuclear cataracts cannot see the tiny smile, while a tailored display can show him the pattern. In this video sequence, one can see how the pattern changes according to the point of focus. Notice that the pattern is only visible when everything else is blurred. We evaluated our displays in 3 rounds. First, on tiny binary images to investigate the suitability for inexpensive LCDs to produce sharp images at retinal resolution for a variety of eye conditions. Second, bigger colored light fields to investigate how an array of those LCDs would be captured by the imaging system. And finally, by user evaluations to check the ability to correct small images on the human eye. We showed that currently available high-resolution displays can create virtual objects at a resolution of about 1 arc-minute, which is the human eye's standard acuity. Our user experiments attest to the display's ability to create corrected versions of virtual objects, and to target specific eye aberrations. According to our testing, users preferred the corrected image up to 98% of the time. Under higher order aberrations, our tests revealed preferences of the corrected image 92% of the time when compared to a non-corrected light field. In conclusion, we presented a new display technology to overcome the need for corrective eyeglasses. It supports spatial and time-varying optical correction with no moving parts using off-the-shelf components and produces results at the retinal resolution.